Welcome to the Deep Dive. We're the show that brings you the crucial, actionable insights from the latest research papers.
Straight from the source.
Exactly. And today, wow, we are attempting something like AI archaeology. We're diving deep inside a large language model.
To its internal world, you mean?
Yeah, to see if we can find evidence of, well, introspection. The big question is, does the LLM have some kind of internal mechanism that tells it, okay, this problem is hard?
Before it even tries to solve it.
Okay.
Not just based on how long the answer turns out.
Precisely. Forget those external proxies. We're looking for an internal signal.
Okay.
And the paper guiding us is really remarkable. It's Probing the Difficulty Perception Mechanism of Large Language Models by Sumbo and Lee and colleagues.
A fantastic piece of work.
Definitely. Okay, so for everyone listening, here's your 1-minute rundown of the key insights. Perfect if you need that quick summary.
Short form version, got it.
First, LLMs, and they specifically looked at Qwen 2.57b Instruct. They seem to implicitly encode how difficult a problem is. It's baked into their representations.
Right, an actual internal signal, not just a theory. Measurable.
Second, this difficulty perception. It's high-dimensional linear, which sounds complex, but it means we can actually detect this direction, the signal, using a surprisingly simple linear probe.
And it works well, doesn't overfit, trained just on the final token representations from the input prompt.
Third, and this is really cool, we can pinpoint where this ability lives. Specific attention heads, right there in the final transformer layer, seem functionally specialized.
Yeah, some light up for easy problems, others have the exact opposite pattern. They specialize in spotting the tough ones.
Fourth, the practical side. This internal perception could be huge for automatically labeling problem difficulty.
Which could bypass the need for expensive, sometimes subjective human annotators when building benchmarks. A big deal.
Huge. And finally, maybe the most surprising bit. This token-level difficulty perception. It doesn't consistently line up with next token entropy.
Meaning the LLM is using something richer, more nuanced than just basic uncertainty about the next word.
Okay, so that's the snapshot.
All right, let's unpack this properly then. Our mission today, I think, is to really dig into the methodology. How did they prove this internal perception exists?
Right.
And then where exactly is it located? Find those components and finally explore what this actually means for building, smarter, more adaptive LLMs.
Let's start with the motivation. Adaptive resource allocation, making the model spend the right amount of effort. That's the goal, right? So why has measuring this internal cost been so hard? Why the reliance on external stuff?
Well, because looking externally is just easier. But as we've seen, it's often unreliable. What we really want is that adaptive token budget.
Meaning?
Meaning we want to avoid the model churning out, say, 4,000 tokens for a simple math problem it could solve in 50. But we also need it to recognize a really complex calculus problem and actually give it the deeper thought, the extra tokens it deserves.
And the ways we've traditionally tried to measure or label difficulty just don't cut it.
Not really, no. Take human annotation. It's generally seen as reliable, the gold standard even, but it's incredibly expensive, it's slow, and, it's prone to subjective bias. What you rate as a 7 out of 10 difficulty, I might see as a 9. Getting large-scale consistency is tough.
Right. And then there are the proxy metrics, like just looking at how long the response is, that's probably even worse.
Oh, absolutely. That heuristic longer output means harder question. It can be profoundly misleading.
How so?
Well, you see these really powerful models, like DeepSeek R1, for instance, they're very capable, but sometimes they generate highly redundant reasoning.
Like they get the answer but keep talking.
Exactly. They might find the correct answer halfway through, but they keep exploring other paths, padding out the chain of thought. It inflates the length artificially.
So the length tells you nothing about the actual cognitive effort involved.
Pretty much nothing, especially for open-ended questions. Length and actual difficulty can have almost zero correlation there.
Okay, so that sets up the core idea of this paper beautifully. Instead of measuring effort from the outside, let's look inside. Let's find a signal the model might already be generating internally.
Yes, using the architecture itself, specifically the attention heads.
And this isn't totally out of the blue, is it? There's prior work suggesting models encode things internally.
Right, exactly. Previous interpretability studies have shown that some fundamental properties, like whether an input prompt is, say, safe or unsafe, often show up in the model's embeddings almost immediately.
Just from processing the input.
Yeah. The information's there, latently, but it's often kind of buried in that high-dimensional space. Hard to see easily.
They did try to visualize it, though. I remember seeing that. They used TSNE on the Quinn model.
They did.
And the results?
Kind of messy. The clusters for easy problems and hard problems were barely separated in those low-dimensional plots, unlike some multimodal models where you sometimes see clearer separations.
So if you can't easily see it in 2D, how did they actually prove this difficulty signal exists?
That's the key insight. The hypothesis was that difficulty perception is high-dimensional linear. Meaning just because you don't see clear clusters on a simple 2D graph doesn't mean the information isn't perfectly structured and separable in the full, say, 758 or 4096 dimensions of the embedding space.
Okay.
Complex behaviors often manifest linearly once you have enough dimensions to work with.
Which brings us right to their main tool, the linear probe. Now, for listeners who maybe don't work with interpretability methods every day, can you break down how this probe works and why use something so simple?
The simplicity is really the whole point here. They used a basic linear regression model. You know the formula y hat equals w transpose h plus b. They trained this very simple model on just the final token embedding, the h, predicting a single number, a scalar difficulty score.
Why linear, specifically?
Because if a straightforward linear classifier can pull that difficulty score out of the final hidden state accurately, it strongly suggests the model already encoded that information linearly during its forward pass. They didn't want some complex non-linear thing that could maybe create the separation. They wanted proof the structure was already there.
Makes sense. And what data did they use to teach this probe what hard actually looks like?
They used deep math. And this choice is critical.
Why deep math?
Because it's a very carefully curated math benchmark. It comes specifically annotated with detailed difficulty labels. And they checked. These labels made sense. They showed that, yeah, if humans labeled a problem as difficulty 8, various models consistently had lower accuracy on it compared to problems labeled, say, difficulty 2. The labels reflected actual task difficulty.
Okay, good validation. But the real acid test for any kind of discovered internal mechanism is generalization, right? Does it work on stuff it hasn't seen before?
Absolutely.
Yeah.
And this is where it gets really, really interesting. They tested the trained probe on out-of-distribution data, specifically GSM-8K.
Which is different how?
Well, if deep math contains complex algebra, calculus, that sort of thing, GSM-8K is more like basic elementary school level math word problems.
Yeah.
A very different domain within math.
And the probe?
It correctly and robustly categorized the GSM-8K problems at a significantly lower difficulty level compared to the deep math tests that it was familiar with.
Wow.
Yeah. It confirms that the linear direction they found isn't just some fluke specific to deep math. It genuinely seems to be capturing a general notion of mathematical difficulty that extrapolates.
So it's not just pattern matching on the training set. It's a real generalizable, difficulty-aware direction in that high-dimensional space.
That's the takeaway.
Okay, so probe works. Difficulty direction validated. The next step is fascinating mechanism interpretability, where inside the transformer block does this ability actually live?
Right. So they used a technique called Headwise difficulty attribution. It's actually quite elegant.
How does it work?
Essentially, they measure the discriminative power of each individual attention head. They do this by systematically ablating, basically zeroing out all the other heads except the one they're testing, head I.
Okay.
Then they take the model's representation with only head I active projected onto that difficulty direction they found earlier and calculate an average score. They then look at the difference, they call it delta I, which is the average projected score for hard problems minus the average score for easy problems, using just that one head.
So a positive delta means that head pushes the representation towards hard.
Exactly. That head is actively contributing to perceiving difficulty.
And a negative delta means it's more sensitive to easy problems.
Precisely. And when they did this for Quen 2.57b Instruct, the patterns were surprisingly clear, especially concentrated in the very last attention layer.
Really? Specific heads stood out?
Oh yeah. They found a distinct set of heads numbers 10, 11, 12, and 13 acting like easy mode sensors. They showed strong negative deltas.
Okay.
And then a completely separate set. Heads 7, 8, 16, and 23 were the hard mode sensors, showing significant positive deltas.
Wow, so clear functional specialization just baked right into the architecture.
It really seems that way.
But correlation isn't causation. They found these patterns, but they had to prove manipulating these specific heads actually caused a change in the model's perception.
Right. That means intervention experiments. ablation studies during inference.
What did they do?
They set up two main interventions. First was difficulty increasing. Here, they muted those easy heads, scaled their output way down by 0.1, and simultaneously amplified the hard heads, scaling their output up by 2.0.
And the other?
Difficulty decreasing was just the reverse.
Yeah.
Amplify the easy heads, mute the hard ones.
And did it work? Did it change the perceived difficulty?
It absolutely did. The difficulty decreasing intervention caused a massive drop in the probe's predicted difficulty score, up to nearly 45% for problems that were originally labeled as moderately challenging.
So they successfully tricked the model into thinking hard problems were simpler.
They did. They confirmed the causal link. But it's the flip side, the difficulty increasing intervention, where they found something really unexpected, a functional deficit. They called it the reasoning collapse.
Reasoning collapse. Wait, I would expect the opposite. If you trick the model into thinking a simple problem is actually really hard.
Shouldn't it try harder, spend more tokens reasoning about it?
Yeah, that seems logical.
That's what I would have assumed too. But no, the studies show that when they used the difficulty increasing intervention on Quen, making it perceive simpler questions as extremely difficult, its average token usage actually decreased.
Decreased? By how much?
By up to about 15% for problems originally rated around difficulty 4.0.
That is profoundly counterintuitive. What does that tell us?
It's a fascinating insight, I think. It suggests that for this specific model, Quen 2.57b instruct, when it internally flags a problem as hitting a certain high threshold of difficulty, it doesn't double down on reasoning.
It gives up.
It seems to hit some kind of self-preservation switch, almost. It aborts the potentially expensive long token generation process earlier. It sees difficulty, token 10, and decides, nope, not worth the compute, leading to this reasoning collapse.
That reveals a lot about the model's default strategy, doesn't it?
It really does. It's not necessarily about deep reasoning under pressure for this model.
Is this pattern universal, though? Do other models like Lama or DeepSeek show the same thing?
Not at all, which is also interesting. They looked at a DeepSeek model derived from Quen DeepSeek R1 to still Quen 7b. It still had the overall difficulty perception ability.
Right.
But the specific roles of those important heads, 10, 11, 12, 13, completely reversed. The wiring was different, likely due to the distillation process it went through.
Okay, different training, different internal setup. What about Lama?
Even more striking, Lama 3.18b instruct showed almost insignificant patterns. Barely any heads stood out clearly in the last layer. Maybe just the 14th head showed a weak signal.
Wow, so what does that imply?
It strongly suggests that things like pre-training quality, the specific data sets used, maybe architectural choices, they heavily influence how cleanly and clearly these functional mechanisms get organized internally.
That really does open up a huge area for interpretability research, doesn't it? Why the difference?
Absolutely, a big question.
Okay, let's shift gears slightly. We've talked about the perception before solving. What about during the reasoning process itself? Does the model's sense of difficulty change as it generates tokens?
Good question. They looked into that by checking the probe's difficulty score at different points in the answer generation. They truncated the responses at 0%, 25%, 50%, 75%, and finally 100% complete.
And what did they find? Is it stable?
Largely, yes. Through the main reasoning phase, say from 25% completion to 75%, the estimated difficulty score stays pretty stable. It seems the model gets a sense of the difficulty early on and sticks with it.
Until?
The only major change is right at the very end. At 100% completion, the difficulty signal drops significantly.
Which makes sense.
Yeah, it's logical. The problem is effectively solved at that point. The task is done.
Okay. This brings us to what you flagged earlier as maybe the most crucial finding, the one that challenges some existing ideas. The relationship between this internal difficulty perception and uncertainty.
Right. Entropy.
A previous work often connects question difficulty with high entropy, meaning high uncertainty about what the next token should be. Do these two things track together here?
And this is where it gets fascinating. At the token level, the study finds they are fundamentally inconsistent.
Inconsistent? How?
Their trends can actually be opposite at times. It strongly suggests the LLM's internal difficulty signal is distinct from and operates independently of simple next token uncertainty.
Okay, we definitely need a concrete example of that. How can a model be certain about the next token, yet still register high internal difficulty?
Okay, think about generating numbers in a math problem. That's the key example they highlight.
Right.
The internal difficulty perception mechanism they found. It showed significantly greater difficulty perception activation right when the model was facing the critical moment of generating the numerical answer tokens.
Makes sense. Those are crucial. What about entropy?
Well, the standard entropy calculation for generating those exact same numerical tokens was often close to zero.
Meaning the model was highly certain, like I'm 99% sure the next token is a 4.
Exactly. Very low uncertainty about the specific token. But the difficulty mechanism was firing strongly.
Why does that difference matter so much? Low uncertainty but high perceived difficulty.
Because it suggests the LLM's internal difficulty signal isn't just about certainty, it's about criticality.
Criticality.
Yeah. The model might be very sure the next token should be 4, low entropy, but because that 4 might be the final digit of the answer, the difficulty mechanism recognizes the stakes. It's like it's screaming internally, warning, this token is critical. If this number is wrong, the entire calculation fails.
Ah, so it's a richer signal. It captures the risk or the importance of getting that token right, even if the choice itself seems obvious.
Precisely. It understands the catastrophic nature of a numerical error in math, even if predicting the number itself feels easy. That's a much more task-relevant signal than just pure next token prediction uncertainty.
That is a huge takeaway. Okay, let's synthesize. What does this all mean for us, for the technical audience listening, looking ahead?
Well, the most immediate practical implication is pretty huge, I think. It provides strong support for using LLMs themselves as objective automatic difficulty annotators.
For building benchmarks, for curriculum learning.
Exactly. We could potentially use a simple linear probe trained on a pre-existing model to categorize the difficulty of new problems accurately and consistently. This could massively reduce the reliance on slow, expensive, and sometimes subjective human labeling.
That alone is a significant contribution. And looking towards future research directions.
Well, that striking difference between Quinn and Lama, why pre-training quality or choices seem to lead to such different internal organizations of these mechanisms that needs serious investigation.
Why are the specialized heads so clear in one model and almost absent in another?
We need to understand that better.
Yeah.
And then there's the application side for optimizing models. Can we use this?
Use the difficulty perception directly. How?
Could this attention head perception mechanism be directly plugged in to advanced reinforcement learning training for reward allocation?
Interesting. Like in processes such as GRPO or DAYS.
Exactly. If we can internally monitor the model's own perception of how hard a problem is, maybe we could design much smarter reward functions.
Encouraging deeper reasoning only when needed.
Yeah, encourage persistence on problems the model finds genuinely hard, while rewarding conciseness and efficiency on the ones it flags is easy. It could lead to much more nuanced training.
For listeners maybe less familiar, GRPO is Generalized Policy Optimization. DAST often refers to dual-stream actor-critic methods. So we're talking about using this newfound introspection to fundamentally change how we teach models to handle the cost versus benefit of thinking harder.
That's the potential, yes.
So the fact that LLM difficulty perception seems real, it's structurally organized in specific components, and critically, it's distinct from simple uncertainty. It just shows how much more there is to understand inside these models.
We're really just scratching the surface of their internal state.
And that divergence you highlighted between perceived difficulty and certainty, between criticality and uncertainty, that feels like the next frontier, both for interpretation and for making these models even better. Something for all of you to think about. Go explore it.